Hello everybody, my name is eMoney at SN2. Welcome back to my YouTube channel. Today we're going to go ahead and start chapter 7. Now, organic reactions are chemical reactions that involve organic compounds. There are several basic chemical reaction types from addition, elimination, substitution, rearrangement, polycyclic, redox, and so many more different reaction types. The focus of this chapter is going to be to discuss elimination and substitution reactions. We're going to cover most other types later on. The essence of chemical reactions is pretty much that you have starting material, say two compounds, a nucleophile and an electrophile, and in the presence of each other, they will interact in some way. Sometimes they'll interact in one specific way, and other types there are two or more different things that will happen. Sometimes there are even side reactions that give us multiple products. We're going to see a little bit of this in this chapter. Now, what's really amazing is to see how molecules interact with each other based on their characteristics. You'll get different reactions that occur depending on how strong or weak your nucleophile is, or based on how substituted your electrophile is. In the real world, if you only want one specific product, you're going to have to manipulate other conditions like temperature or solvent or catalyst to control desired outcome. And we're going to talk about all of this in this chapter. And we're going to focus on 4 big reactions that you see that I have summarized here in this one page. We're going to talk about SN1, SN2, E1, and E2. And we're going to get into the details of each one. All right, and we're going to do lots and lots of practice problems in this chapter. Usually students find that organic chemistry gets exponentially harder when they get to chapter 7 and onwards, not because the material is necessarily difficult, but because it is a lot of information thrown at you very quickly. All right, so in this chapter, we're going to talk about substitution and elimination reactions. We're going to spend time on each one of this. You can print this page out, cut it up, make them flashcards, and as you learn one reaction like SN2, check off, do you understand all the things that make up an SN2 reaction, right, in its respective box, and so on and so forth for all the reactions here. Now, this chapter will focus on reactions of alkyl halides. So, sp3 carbons attached to halogens. All right, we're going to start this discussion by talking about SN2 reactions with alkyl halides. That's going to be our starting place for this chapter. All right, but let's really quickly redefine nucleophile and electrophile in case you forgot. All right, a nucleophile is a nucleus-loving molecule. It's going to either have a negative charge or a lone pair, all right? And it's going to be the attacker, if you will. All right, and we're going to see some examples shortly. On the other hand, electrophiles are electron-loving. They usually have positive charges, and they get attacked by nucleophiles. In regards to our discussion here in this chapter with alkyl halides will act as our electrophile, and we're going to learn a range of nucleophiles that will result in a variety of different substitution and elimination reactions. All right, now on to SN2 reactions, okay? I want to start by giving you a thesis statement for our discussion today. All right, when treated with a nucleophile, an alkyl halide can undergo a substitution reaction in which the nucleophile replaces the halogen. All right, we're going to break this statement down into several pieces and build a profile for SN2 reactions like you saw in the SN2 box in the previous page. All right, but before we dive into this thesis statement, there's 2 questions that we need to ask and answer. All right, what we have here, all right, this is an alkyl halide, right? Why? Because we have this carbon that's attached to a halogen, all right? Now, our question is, why is the carbon, this carbon that I've circled in red right here, why is it susceptible to being attacked by a nucleophile, all right? remember, we just said that our alkyl halide will usually act as an electrophile in this chapter. That means it's getting attacked. All right, and it's getting attacked usually in regards to, say, SN2 reaction at the carbon that is attached to the halogen. Why is that carbon next to the halogen susceptible to being attacked by a nucleophile? Well, that's because the halogen here, all right, the halogen here withdraws electron density via induction. All right, it's more electronegative. It withdraws electron density towards it. All right, giving this carbon here a partial positive charge. And this partial positive charge makes that carbon susceptible to being attacked. In addition, halogens usually are going to act like really good leaving groups because they are stable bases. So when we cover SN2 in more details, when we treat this alkyl halide with a nucleophile, all right, our nucleophile is going to come in and attack this carbon, all right, because it's electrophilic, all right, and then it's going to attach itself to the carbon, but in order to do that, it has to kick out the halogen, right? That was essentially our thesis statement for SN2. All right, and don't worry, we're going to actually talk about this in detail. Now, the second question before we get into SN2 in more detail is, how do we locate, when looking at an alkyl halide, alpha and beta positions? This is going to prove to be important for us to know, all right? So how do we assign alpha and beta positions on an alkyl halide? And then how do we assign the alpha position to be primary, secondary, or tertiary, and so forth for the beta position? So let's look at our alkyl halide here again, all right? The carbon directly attached to the halogen is the alpha position. So this is the carbon directly attached to the halogen. That is the alpha position. Any carbons attached to the alpha carbon are beta carbons. So what carbons are attached to this alpha? Well, we have a carbon right here. All right, we're going to highlight it in orange. That's a beta carbon. And look here, we have another carbon attached to the alpha. That is a beta carbon. Now, how many groups are attached to each carbon, not counting hydrogens, is how we assign the labels of that carbon being primary, secondary, or tertiary. All right, so now that we have this basic information down, we know, we've reminded ourselves what a nucleophile, what an electrophile is. We know how to identify alkyl halides. We know how to assign alpha and beta positions, and then how to go about assigning primary, secondary, or tertiary assignments to those positions. Now, with this basic information, which we will obviously build on more with practice problems, we can start to quickly go over these two very important details and then finally get into SN2. All right, so here what we have, and this table is shown, actually, these tables are shown at the end of the David Klein textbook in chapter 7, but I think that you should look at it before you even start this chapter, before you learn SN2, SN1, E1, and E2. All right, this first table right here, all right, helps you kind of categorize certain molecules under categories of strong base, that's a weak nucleophile, strong base, that's a strong nucleophile, weak base, that's a strong nucleophile, and weak base, that's a weak nucleophile. All right, so under each of these four categories, there are example molecules, all right, that are important for you to understand and memorize potentially, all right? So if you're thinking, okay, well, we're going to learn SN2, all right, and we're going to learn that in SN2, we're going to need, say, for example, a strong nucleophile weak base, all right? We know for an SN2 reaction that we need a strong nucleophile weak base, all right? So we can go into this category and we can see a bunch of strong nucleophile weak bases that will initiate an SN2 reaction, all right? And being able to recognize these nucleophiles and bases is important for figuring out what you need For what specific elimination and substitution reaction? All right, we're going to come back to this chart every time we learn a substitution or elimination reaction. All right, now we can start the story of SN2 reactions. All right, this story goes as such. A strong nucleophile that is also a weak base, all right, meets a nice electrophilic carbon attached to a halogen. All right, this strong nucleophile meets a nice alkyl halide. This is the start of a love story. In this fairy tale, the strong and handsome nucleophile attacks, or as one would say, hits on the electrophilic carbon attached to a halogen, which is our leaving group. Now, after the electrophilic carbon gets hit on by the strong and handsome nucleophile, she falls in love immediately. She dumps the halogen, all right, our leaving group leaves, and she gets with the nucleophile instead. Now, this is very important. This happens very fast and all in one step, and we know this because we can observe the energy diagram for SN2 reactions, and what you notice is it demonstrates one transition state, no intermediates, all right, to suggest more steps. Now, you might ask, well, what does this love story really look like? All right, we talked about the fairy tale in words. Now let's look at it in play. All right, so here's our strong and handsome nucleophile. All right, and he got his eyes on this electrophilic carbon that is attached to a halogen. This is our alkyl halide. All right, and this is our nucleophile. All right, our nucleophile falls in love with our electrophilic carbon here. All right, and decides to hit on her. All right, attack her or hit on her. All right, now this electrophilic carbon, she has a boyfriend. All right, it's this halogen group, but she wants to get with a nucleophile, so she dumps the halogen and gets with the nucleophile instead. All right, the halogen leaves, she gets with the nucleophile instead. All right, the way you draw these arrows for this reaction is as such. All right, the nucleophile, you draw an arrow to the carbon that it attacks. All right, the carbon, the bond between the carbon and a halogen breaks. All right, you want to draw it at the bond here. All right, the halogen group leaves, it goes bye-bye. All right, and instead we attach the nucleophile to the carbon. Remember, this happens in a concerted fashion, one step. All right, now you might ask, what are examples of strong nucleophiles that are also weak bases? All right, here's a list. All right, here is a list, and we can go back here to our table. All right, here is a list of potential bachelors, right, for the electrophilic carbon. All right, so these weak bases, strong nucleophiles, and right here, let's draw a box around them. All right, let's draw a box around them right here. All right, these are all strong nucleophiles, weak bases, which is what you need. You need a strong nucleophile for an SN2 reaction. Also note here, that the halogen is primary or secondary, and there are no side products with SN2 in that regard. All right, so really quickly, and we can look here at the table. If you have a strong nucleophile weak base, which can be any one of these 7 strong nucleophile weak bases, all right, if you have any of these strong nucleophile weak bases, all right, and your alkyl halide is primary or secondary, you will always only get SN2 reaction that occurs, and you will only ever get SN2 products. All right, now you might ask, why is this reaction called SN2? All right, that's a very good question. Well, the S stands for substituted, N for substitution, N stands for nucleophile, and there is a 2 here at the end because this reaction is bimolecular, meaning the step involves 2 chemical entities. For biomolecular reactions, the rate equation is actually written as the rate constant plus the concentration of the alkyl halide and the nucleophile. That means that the rate of the reaction depends on both alkyl halide and nucleophile, hence the 2 there. All right, now let's do a quick example problem here. All right, quick example problem. Let's look at this. All right, we have our alkyl halide here. All right, we have an alkyl halide and we have a nucleophile. All right, so let's label this. Here's our alkyl halide. Beautiful. Here's our nucleophile. All right, actually the nucleophile part that's going to be reacting is the Cl minus. All right, so we have our alkyl halide. Our alkyl halide, let's write some information about it. All right, here's the carbon that's attached to the halogen. How many other groups are attached to this carbon? All right, one other carbon group. All right, so this alkyl halide, by the way, is primary. All right, we have our nucleophile. It's Cl minus. If you look at the table, Cl minus, this is a strong nucleophile, weak base. All right, so we know for sure, based off of what we've written here, that what's going to occur is an SN2 reaction for sure. All right, now how do we draw this reaction? Well, the negative charge of chlorine will come here. It's going to hit on that electrophilic carbon, right? Electrophilic carbon, right? The halogen group leaves, she dumps them. All right, and then we attach the chlorine there instead, and the iodide has left. It's our leaving group. It got broken up with, if you will. All right, so that's how we draw that reaction. Now, what happens if we double the concentration of our nucleophile? All right, this is what it's saying. Double the concentration of NaCl, our nucleophile. All right, we double it. And what if we triple the concentration of our alkyl halide? All right, what happens? Well, if you're doubling your nucleophile and tripling your alkyl halide, this reaction, if you multiply these two numbers, this reaction would go 6 times faster if you doubled the concentration of your nucleophile and tripled the concentration of your alkyl halide. You have to multiply these two because remember, our rate depends on the concentration of our alkyl halide and our nucleophile. All right, now to summarize, for purely SN2 reaction, no other side products, we need a strong nucleophile that is a weak base. All right, we need a strong nucleophile that is a weak base, and that will always give us SN2 if our alkyl halide, the alpha carbon at our alkyl halide is either primary or secondary substituted. Okay, so if we have a strong nucleophile weak base and our alkyl halide, the alpha carbon in our alkyl halide is primary or secondary, we will always get SN2. Okay, now here's something that's a little different. All right, here's, by the way, our strong nucleophile weak bases. There's something we need to add here. What if we have a strong nucleophile, strong base? All right, well then the answer to that, what will happen is you're still gonna get SN2 products, but you're also gonna have other products. Okay, these are examples of strong nucleophile, strong bases. All right, if your alpha carbon is primary, your major product is still SN2 with a strong nucleophile, strong base. You will get some E2 products though. No worries about that yet. We're gonna cover E2 in the next lecture. All right, if it's secondary, if your alpha carbon in your alkyl halide is secondary, you will still get SN2 product, but it's not the major product. Your E2 product for the reaction will be. All right, so keep that in mind. This is why it's important for you to know how to recognize your nucleophiles and how to recognize how substituted is your alpha carbon, because those two pieces of information are going to help you when you look at an alkyl halide and a nucleophile to determine what kind of reaction is going to happen. Is it just SN2? Is it SN2 and something else? So that you can draw all the right products for the reaction. Okay, and we're going to do so many practice problems for this chapter, all right? Hopefully this is conceptually starting to sink in though. Now, another question. What if our alkyl halide has a chiral center? What happens if we attack, the attack site is chiral for SN2, okay? We're still speaking about SN2. Well, the reaction for SN2 is said to proceed with inversion of configuration. So this strong and handsome nucleophile, all right, is going to attack from the backside. All right, if you have a chiral center at your alpha carbon, all right, the strong and handsome nucleophile is going to attack from the backside at your electrophilic alpha carbon. And what you get is a change in the chiral center in your product. All right, so here is our alkyl halide starting material. All right, here is our carbon, our electrophilic carbon. All right, the configuration for this site is R. Okay, so here's our nucleophile. It's going to come and attack this electrophilic carbon. All right, the halogen will leave and it'll be replaced with chlorine. All right, but because this is a chiral center, your product is going to have the opposite configuration. Hence, why SN2 proceeds via inversion of configuration. So if you're doing an SN2 reaction at a chiral center, your product will have the opposite configuration. So if you start with R, you'll get S. If you start with S, your product will be R. Now, the backside attack happens because it's easier for the nucleophile to approach it that way. All right, this has to do with molecular orbitals associated with the molecule as a whole. All right, it allows for efficient overlap between the HOMO of the nucleophile and the LUMO of the electrophile when a backside attack occurs. All right, in other words, you can also think of it kind of steric interactions as well, if you will. All right, now, another thing about SN2, all right? But before we get there, let's do a few practice problems, all right? This is good. We need to do some practice problems. All right, draw the product for each of the following SN2 reactions. All right, these problems tell us we want to draw the product of an SN2 reaction. Beautiful, all right? So we're going to start off with A, and here I have just a little write-up of how you want to approach these problems, all right? When solving problems, you want to draw your reaction scheme, all right? You want to identify where's your nucleophile, where's your leaving group, all right? Then you want to say, what kind of nucleophile do I have? How substituted is my alpha carbon? Then you want to ask yourself, what kind of reaction will take place? What's my major and minor product? All right, and this is special for SN2. Do I have a chiral center? Because then I need to draw inversion of configuration product. And then you want to draw the rest of the reaction scheme. So we're going to do all these steps for A. All right, what we have here is 2S chloropentane. All right, so and then we have NaSH. So first step, we're going to draw our reaction scheme in regards to our starting material. All right, so pentane, 2-chloropentane. So let's draw pentane. 1, 2, 3, 4, 5. That's 5 carbons. And at position 2, we have a chlorine group. So right here we have a chlorine, and it's going to be S configuration. All right, so that's going to have, all right, a dash. Okay, here we have S2 chloropentane. Perfect. Now, here's our nucleophile, NaSH. It's really just SH minus here, okay? So we've drawn our alkyl halide. Let me write this in a different color. We've drawn our alkyl halide. We've drawn our nucleophile. Beautiful. All right, so that means for step 2, we've identified our nucleophile as this, and we know that the halogen is going to be our leaving group. All right, beautiful. Now, what kind of nucleophile do you have? Now, the question is nice. It tells us it's going to be SN2, but let's pretend we didn't know that. All right, what kind of nucleophile do we have here? Well, we can go back to our table. All right, I'm going to scroll back to our table so we can get used to looking at our table. SH minus. Hey, look, that is a strong nucleophile weak base. All right, we're going to scroll all the way back down here. We're going to write that. This is a strong nucleophile weak base. Fantastic. All right, so that's done. These first three steps are done. Let's look at 4. 4 asks us, we need to figure this out. How substituted is our alpha carbon? All right, here's our alpha carbon. How many other groups is it attached to besides the halogen? We don't count it, or any hydrogens. Well, then it's attached to 2 different groups. All right, so this alpha carbon, and we're going to write this, the alpha carbon is secondary. All right, we have a strong nucleophile weak base and our alpha carbon is secondary. What kind of reaction are we going to have? Let's go back to our table. We have a strong nucleophile weak base. All right, so we're looking at this column and it's secondary. Oh, that leads us to SN2. The reaction that's going to happen here based off of our nucleophile and how substituted our alpha carbon is going to be an SN2 reaction. And we're only going to get SN2 products, right, based off of our table. So now we're confident. All right, we know the textbook people didn't mess up writing this statement. All right, we know for sure, based off of what we know, this is going to be an SN2 reaction. All right, SN2. All right, now before we proceed with drawing the reaction, all right, quick question. We know it's SN2. Do we have a chiral center? Because we have to be very careful if we do. The answer to that is yes. Obviously, we have a chiral center. The name of the alkyl halide pretty much told us that, right? That it's going to be S configuration. That means our product, because SN2 follows inversion of configuration, our product has to have an R configuration at the chiral center. Guess what? We have all the information we need now to finally draw the reaction mechanism. All right, so we're going to go ahead and we're going to draw it out. All right, here's our Cl. Here's our SH. All right, here's our nucleophile. It's hitting on our carbon. All right, she dumps her chlorine best friend. All right, she dumps her chlorine boyfriend, sorry. All right, and now she starts dating nucleophile SH. Now remember, inversion of configuration. So we had S here, we need R here. So that means if we had a dash here, we want a wedge here. All right, and the chlorine has left the scene. All right, and that's how we draw the reaction mechanism for this SN2 reaction. Fantastic. All right, let's do one more just for good measure. All right, let's do one more for good measure. Let's erase this so we can have some space, and let's go through all the steps again for B now. All right, now this might seem super easy, but that's only because we've only learned one reaction here, SN2, right? When we learn all 4, SN2, SN1, E1, E2, it's going to be really beneficial to go through all these steps, right? It's kind of obvious now because we know we're only doing SN2 because that's all we've learned so far in the chapter, but these steps are really going to help you figure out how to draw your products for reactions, okay? Let's look at B. B says we have R3 iodohexane. Beautiful. Let's draw hexane. 1, 2, 3, 4, 5, 6. All right, at position 3, we have iodine, and it's R. All right, so to get R, we'll need wedge. And you can always check if you're not quick with drawing, figuring out how to draw our S configuration at a site, take it easy, do it step by step, all right? And go back to chapter 5 where we covered this, all right? Now, here's R3, all right? So the R3 iodohexane, okay? So here's our alkyl halide, beautiful, all right? And our nucleophile here, NaCl, it's just going to be Cl minus, all right? This is just because ionic, the sodium there is just to balance the charge, all right? But the Cl minus is what's acting as our nucleophile. All right, so we've drawn R. Let's start this new checklist over. All right, we've drawn our starting materials. We've identified our nucleophile, and guess what? This iodide, this is a halogen, this is our leaving group. All right, what kind of nucleophile do we have? What kind of nucleophile is this? All right, if we go back to our chart, all right, Cl right there. It's a strong nucleophile, weak base. Beautiful. We're going to go ahead. We're going to write that. All right. It's a strong nucleophile, weak base. Fantastic. Now, how substituted is our alpha carbon? Well, our alpha carbon is right here. How many other groups is it attached to? 1 on this side, all right, and 2 on this side. This is secondary. So our alpha carbon is secondary. Now, again, if we have an alpha carbon that's secondary and we're dealing with strong nucleophile weak base, all right, this is absolutely an SN2 reaction. All right, we're only going to get SN2 products. All right, so we know it's SN2. All right, now, before we draw the reaction, we have to ask, because this is SN2, do we have a chiral center? The answer is yes, we absolutely do. It is right here. All right, and it's R. So that means our product has to have S. Okay, so now we know everything to go ahead and draw this reaction. So let's go ahead and do that. All right, here's our starting material. Here's our nucleophile. Nucleophile is going to come and attack our electrophilic carbon. Halogen's going to leave. All right, and what we get as an end product. Now this is R, so we need S. So that means if this is dash, this will be a wedge, and our chlorine group is here, and the iodine obviously leaves. It's been dumped. Okay? And that is how you would go about step by step to answering these kinds of problems. All right? Fantastic. Now, let's do one more for good measure here. All right? One more for good measure, guys. So, again, here's our starting material. All right? Here is our alpha carbon because it's attached to this halogen, which is our leaving group. All right? Ignore the Na, N3 minus. This is our nucleophile. All right? Now, this is a strong nucleophile, weak base. All right? And our alpha carbon is 1, 2, is secondary. All right? So we have all the ingredients for an SN2 reaction. All right? Now, before we get carried away and draw the mechanism, do we have a chiral center? Yes, we do. We have a chiral center. All right, so this bromine is, let's see, 1, 2, 3, bloop. That's R. This S, so we want to draw the product as R. All right. In other words, if it's on a dash, our nucleophile is going to replace it on a wedge. All right, so we're going to go ahead. We're going to draw this really quickly. All right, here's our bromine. Here's our nucleophile. Strong nucleophile, weak base, going to attack the carbon. Halogen leaves. All right, and now our final product is going to look like this. And our bromine has left the chat. All right, fantastic. Okay, so that's how you want to approach these kinds of problems. Now, really quickly, all right, really quickly, just to reiterate, all right, the rate of an SN2 reaction, all right, process is going to be extremely sensitive to the nature of the starting alkyl halide. All right, so presence of substituents at the alpha or beta position can really reduce the rate of the reaction. All right, the rate of SN2 reaction is most sensitive to the number of substituents at that alpha position. All right, so what that means here is looking at this really nice table. All right, now if at our alpha position we just have a methyl group, all right, and then if it's primary, if it's secondary, or if it's tertiary, as you notice here, all right, as you increase the number of substituents at the alpha position, look at how our relative rate of the reaction just keeps decreasing. All right, so as you add groups to your alpha position, if there are a lot of substituents at that alpha position, the rate of the reaction is just going to get slower and slower for the SN2 reaction. The beta position also has the same pattern here. All right, if your beta position is just a methyl, if it's primary, if it's secondary, or if it's tertiary, what you notice is as you increase the number of substituents, look at how our rate decreases so much. All right, So that's really important to know. See, SN2 with a methyl substituent, look at how small your activation energy is. Very small. So the reaction is fast. All right. That's with a methyl substituent. With a primary substituent, look, our activation energy is higher. It takes more to get the reaction going. So it's going to be slower. All right. Secondary substituent, even slower. All right. And if we had tertiary here, it would be the slowest. All right, so that's really important to remember. Let's do a quick problem here. We want to rank the alkyl halides in order of reactivity towards SN2 reaction. So we're going to focus on the same carbon, right? Obviously, our alpha carbon that's attached to our halogen here. All right, and we're going to write how substituted the alpha position is. All right, here it's just 3 hydrogens, so it's just a methyl group. All right, here, all right, we have another carbon group, so this is primary. All right, at this alpha carbon, it's attached to 2 other carbons, secondary. And this alpha carbon is actually attached to 3 carbon groups, so it's tertiary. All right, so we have a methyl, we have primary, secondary, tertiary. What is going to be the fastest? All right, what's going to be the most reactive? This methyl is going to be the most reactive. All right, it's going to have the fastest SN2. Fastest SN2. And you know what? It just decreases as we go down here. All right, so this is going to be the least reactive. This tertiary is going to be the least reactive. It's going to be the slowest mechanism for SN2. All right, so the more substituted your alpha position is, the slower the SN2 reaction is. All right, and that might be a conceptual problem in an exam, so it's really good to also understand the effect of substitution on the rate of these reactions. Now, one more thing before we wrap up everything we need to know about SN2. We've built this whole profile. All right, this is going to be the last thing we need for our profile. What are the solvent effects on SN2 reaction? Now, know for SN2, your nucleophile and leaving groups are ionic. So that means polar solvent is required for these reactions. Now, there are 2 types of polar solvents. You have protic polar solvents and polar aprotic solvents. All right, SN2 reactions are better off and faster with polar aprotic solvents. These solvents are better for SN2 because it won't solvate both the negative and the positive charges, only the positive. And guess what? That leaves the negative charge associated with the nucleophile free to react. That means, in other words, the nucleophile is left unstable and wanting to react. And if that's the case, then an SN2 reaction will happen successfully, which is why for SN2, the preferred solvent is polar aprotic. It solvates the ionic species, and there's no hydrogen, so it doesn't get in the way of the reaction. All right, so those are all important things to remember. All right, so with that being said, let's quickly finish this off with a few practice problems in regards to solvent. Okay, which of the following reactions is expected to produce the end product 1-propanol at a faster rate? Explain. So here we have sodium hydroxide. This is our nucleophile in both cases. All right, and then we have water versus DMSO. Which is a better solvent for SN2 reaction? Well, let's categorize this. Water is what? Water is a protic solvent. All right, so it's a protic solvent. DMSO, on the other hand, is what? Well, if we go back up here, DMSO is right here, dimethyl sulfoxide. It's polar aprotic, which is obviously better for SN2, polar aprotic. So this reaction will happen at a faster rate, all right, and more successfully. All right. Also, what could have been a factor for faster rate is if our starting material was different. Then we would want to see how substituted our alpha carbon is. All right. We don't have to worry about it here. we don't have to worry about how substituted our alpha position is here and compare because they're both the same starting material. All right, I'll let you do 7.9 yourself. Let me know what you think the answer is in the comment section below. That is all for SN2. We should be SN2 masters now. Please do practice problems in your free time. Even a little bit goes a long way. Next time, we'll talk about E2 reactions. Other than that, good luck, happy studying, and have a beautiful day.